So hi everyone, my name is Rob Rieben. I'm the lead for the Multiphysics on Advanced Platforms project. And I want to acknowledge my co-authors on this, Arturo Vargas, Tom Stitt, and Kenny Weiss. And of course, we're presenting work on behalf of the entire MAPP team. Next slide. So, by means of introduction, at the DOE laboratories, we do high energy density physics experiments, and these require complex multi-physics simulations. To model these, sort of a minimum set of physics you need is radiation magnetohydrodynamics. So this is multi-physics. We're dealing with multi-material all-speed fluid mechanics, covering all phases of matter. This is compressible flow, so we have shock waves. We have complex material properties that we have to consider. And for fluid mechanics, we rely on explicit time integration methods. Now we couple this with radiation diffusion or transport, as well as magnetic diffusion. Typically, this is done by force energy exchange with the fluid. And we consider 3T plasma physics, where we have separate temperatures for radiation, electrons, and ions. And we also produce thermonuclear fusion reactions. And when we're coupling these implicit physics with the explicit hydrodynamics, we use so-called IMEX methods to do that. Now, we employ a diverse set of algorithms to solve these coupled physics problems. Typically, we're doing arbitrary Lagrangian Eulerian methods, but we also utilize direct Eulerian methods, particle methods, and Monte Carlo methods. And of course, all of this has to work on unstructured AMR meshes, as well as higher order. That's a relatively new thing at Livermore, thanks to MFEM. And the applications for this include inertial confinement fusion, like what's done at the National Ignition Facility at Livermore, but also pulse power experiments like those done at Sandia, as well as equation of state and material strength experiments. And so for all of these cases, our goal is to model and ultimately predict the behavior of complex physical systems. Next slide. So MARBL is a new multi-physics code that's being developed at Livermore. It started around 2016. It is a next-gen ICF pulse power code that's part of this MAPP project that I'm discussing. It's based on a couple of things, notably higher order finite element methods, but also modular physics packages. So we have a higher order finite element capability. That's the BLAST code that you've heard Zanio talk about. But we also have support for higher order finite difference Eulerian. We support 3T multi-group diffusion with TN burn, and we're actively developing new physics components. But of note for this workshop, we leverage a lot of modular infrastructure that's developed at the laboratory, including MFEM for finite elements, and it's our primary source of mesh field and operator abstractions. We also utilize a library at Livermore called Axum, as well as the CIDR conduit data layer, which has support for MFEM as well. And the key point of this project is that it's heavily based on higher order numerical methods. Higher order methods have higher resolution accuracy per unknown, but perhaps a more important property in the context of exascale computing is that they have strengths that play to GPUs. They have higher flop to byte ratios, which means we have better throughput on GPU architectures. Next slide. So we believe MARBL represents a unique capability. Here's an example of a 3D higher order AL simulation. This is around 115 million quadrature points run on 96 GPUs. And as I'll show throughout this talk, we do, as a result of a lot of hard work, we are able to get up to 15x GPU versus CPU node speed up. Next slide. In this example, material properties are evaluated at element quadrature points. So this is using the MFEM quad point concept. Next slide. These are higher order unstructured elements, and so we get subcell resolution and curved elements. Next slide. We take advantage of the mesh optimization algorithms in MFEM, particularly the TMOP algorithm, which is now GPU accelerated. Next slide. And we're of course very interested in GPU parallel performance, and here we're using the Raja abstraction layer in conjunction with MFEM, as well as matrix-free partial assembly methods. Next slide. And we couple this with some Livermore tools for doing in situ volume rendering on the GPU. So this is an example of the Ascent library. Okay, next slide. As part of a tri-lab, so that's Los Alamos, Livermore, and Sandia, L1 milestone, that's just a big 5-year milestone. We were able to demonstrate successfully scaling our code to half of the Sierra machine at Livermore and all of the ARM-based Astra platform at Sandia. We were also able to demonstrate 15x GPU speedup when we compare node-to-node performance. So at the TriLab, at the NNSA labs, we measure speedup on a node-by-node basis, which means if we're comparing one Sierra node, we use all the resources available. That would be 4 GPUs compared to one CTS, which stands for Commodity Technology System. In this case, that would be an Intel Xeon with 36 cores. So that would be 36 MPI ranks versus 4 GPUs on 4 MPI ranks. And when we do that comparison, we can achieve greater than 15x speedups. We've also done comparisons on the ARM-based Astra system. And so what we're showing here is both strong and weak scaling of the code out to very large node counts and very large GPU counts. Next slide. So going into a little bit of details here are some strong combination strong and weak scaling plots on the Astra machine. That's in green at the top. So you can see that we were able to scale out to all of Astra. That's approximately 2,500 nodes with 54 MPI, or sorry, in this case, OpenMP tasks per node. And in red, we've got the Sierra machine where we scaled out to half of it, utilizing approximately 8,000 GPUs. Next slide. So what I want to point out here, and I want to spend some time talking about, this is throughput. You've seen this in Zanio's talks when he talks about performance. This is the number of H1 DOFs processed per cycle per second. And so higher is better. It means you're able to process more unknowns per problem size. And what we're showing here is the same benchmark problem with an increasing size, and then running on our commodity technology systems. That's the black lines, and then our GPU-based system, Sierra, those are the red lines. And we're varying the order of the elements, but we're keeping the total number of unknowns the same. And what you can see is that higher order methods, particularly the dark red line, perform the best. We get more throughput when we use higher order methods, especially on GPU systems and especially as the problem size increases. Next slide. So in MARBL, we utilize a higher order ALE algorithm. ALE has 3 phases. You solve the fluid conservation equations on a moving mesh. That's the Lagrange phase. Then you change the mesh through some mesh optimization procedure, and then you must conservatively and monotonically remap your field variables onto that new mesh. So those 3 phases together, Lagrange phase, remesh, and remap, comprise ALE. And we've been pushing really hard on using matrix-free partial assembly methods for each of these phases. So on the throughput plots below, it's the previous data set, but broken down by phases. And what you can see is that for the 2 phases that we currently have with partial assembly, we do in fact achieve better performance as we go up in order. This is an expected result, but it's very exciting to see this in a large scale application on a GPU platform. The remap phase is currently based on full assembly, but there is an active set of development taking place to convert this to partial assembly. And you can see in this plot here that the cubics are not performing as well as the quadratics, and that's also expected. That's what we would expect for full assembly. We expect this to change, though, once we fully convert this to partial assembly. Next slide. So enabled to achieve GPU performance at scale in a large multi-physics code like this, it really requires coordinated efforts. It requires the right algorithms. So when you deal with higher order finite elements, these partially assembled matrix-free methods are really the way to go. You also need portable kernels. So we use Raja at Livermore, and there's been a tight co-design process with Raja and the MFEM library to enable Raja support. You need efficient memory management. That's something that MFEM provides. We also utilize a memory utility at Livermore called Umpire. So MFEM supports Umpire. We extensively leverage our performance analysis tools that are developed in-house. So that's Caliper, Spot, and Hatchet. But we also use our own tools as well, including Jupyter Notebooks. And then I guess the point I really want to emphasize here is that in order to make this all work, you need interdisciplinary teams to work together. So you need physicists, mathematicians, computer scientists, engineers, all working closely on the team. And I want to just point out that all of the software libraries that I mentioned here are open source. MFEM, of course, you're aware of, but I wanted to point out some of these other Livermore developed open source libraries. Next slide. So the way we do portable kernels in MARBL, we use a DSL macro layer that basically utilizes Raja underneath. And at a very high level, you can think of Raja as taking a standard C-style for loop and then introducing a templated loop execution. So now we've abstracted how we execute that loop. And it's templated on something called an execution policy. That can be OpenMP, that can be CUDA, that can be something to work with an AMD GPU. And then what's typical in most of our codes at Livermore, we take an extra layer of abstraction and put sort of code-specific wrappers around that. And so that's what this blast for all does. But the point of using Raja in code is that the loop body does not change. It's really just the abstraction of the loop traversal that changes. Now, if you just start with the basic for loop and use a Raja for all, that's a good starting point for performance, but it's really not sufficient when you have more complex loops and kernels. Next slide. So working closely with the MFEM and the Raja teams, there's a new abstraction in Raja that's called Raja Teams, and it's well suited for nested for loops. So if you want to get high performance in a nested for loop and take advantage of GPU shared memory, Raja Teams is the way to go. So here's some high-level source code, just giving you an idea of how this works. And again, you can wrap this in sort of a macro to help make it specific for whatever code you're working in. And this abstraction resulted in much cleaner code and really led to better device utilization, as I'll show on the next slide. Next slide, please. So yes, because we're using higher order elements, these map very nicely onto GPU thread blocks, and Raja and this new Teams abstraction plus MFEM really enables that. I wanted to point out our porting timeline at the top here. Getting GPU performance in a code takes a lot of work. We definitely benefited from all the hard work that went into MFEM and all the open source software development at Livermore. But getting this into the code, usually the first time you try to run on a GPU, things run slower. But you reach a point called break even where you're able to match the performance of one GPU enabled node versus a standard node. And from that point on, you can begin to make even more improvements. And so over the course of about a year, we went from basically running slower on the GPU to hitting break even to now crossing the 15x and greater today speed up line. Okay, next slide. So here's an example of this Raja-based teams approach. So if we just take one of our standard benchmarks, actually this is a seed benchmark that Zanio had mentioned. And if you run with a Raja for all, you can see on the left that the performance is not so great compared to native CUDA. But if you use the Teams abstraction, you can match native CUDA, but still have this performance portable kernel that can target other GPUs. Next slide. So in addition to a lot of hard work in porting kernels and tuning, it was really important to take advantage of performance monitoring to get the code ported. So we made heavy use of a tool developed at Livermore called Caliper, which, as you heard Zanio mention, MFEM now has support for that. So Caliper is a very lightweight library that you can use for monitoring performance of your application, including any linked libraries that also have Caliper support. We also have a tool called Hatchet. You can think of it as a post-processing tool that can take Caliper data and give you speed up and slow down reports. So using Caliper and Hatchet, we were able to closely monitor the performance of our code, find the hotspots, work on porting those GPU kernels, and tuning the performance over that year that I described. Next slide. Spot is a tool developed at Livermore that can be used to track the performance that something like Caliper generates. So as we were doing this work, we used Spot to store all of our runs, all the data from our runs, performance data. And this allows you to very nicely over time see trends in performance. So you can see over the course of several months, our performance was improving. So runtimes are decreasing. And with a tool like Spot, you can take slices. You can take arbitrary slices of this data. That would be the plot on the bottom. And you can use that to highlight places that need further improvement. And so in this example, the long green line that was the mesh optimization that started to become the long pole in the tent. And so that was what led to a lot of the work in developing GPU performant mesh optimization in MFEM. Next slide. And then I want to mention, it's also really important when working with GPU systems, managing the memory, especially host device transfers, and utilization of memory pools is really important. So at Livermore, we have a library called Umpire that we've been using quite extensively. The MFEM version 4.0 also introduced a very nice memory manager that works in collaboration with Umpire. And this allowed us to utilize memory pools. So this helps, memory pools on the GPU help in several ways. It allows you to eliminate repeated allocations because mallocs on the GPU can be very expensive. It also allows buffer reuse. So if you have multiple libraries that are sharing GPU memory, this allows you to pool your resources. And I think, again, I just want to emphasize that MFEM now supports this, and this has been very beneficial for our project. Next slide. So putting it all together, we can now run higher resolution 3D higher order AL simulations on our GPU systems and achieve substantial speed up. So could you play that movie on the left? This is a, oh, it's not playing?
Did not work.
Maybe because it's streaming from the website. Yeah, it looks like it's kind of pixelated.
Yeah, I'm sorry, this doesn't seem to work.
That's okay.
I can pull the talk locally.
On the left is a multi-material simulation of a shape charge. This was run on 24 GPU nodes, so 96 GPUs, used about 115 million quad points. Oh. There we go. Thanks.
Sorry about this.
Perfect. Yeah, that looks great. Yes, so you can see the evolution of the shockwave driving the jet formation in the copper liner. And then if you play the movie on the right, this is an idealized, simplified ICF benchmark that's used to illustrate Rickmeyer-Meshkov and Rayleigh-Taylor instabilities. Could you play that again? In both of these examples, we're utilizing, of course, matrix-free methods pretty much across the board, with the exception of the DG remap. And this is also utilizing TMOP running on the GPU. Okay, I'll let that play one more time. Okay, thanks. So yes, and then I just wanted to point out that in both of these examples, we are utilizing the higher order mesh optimization features of MFEM to dynamically track materials and interfaces. So on the example on the left, we're dynamically tracking materials. So TMOP enables you to specify regions that you'd like to do R adaptivity. And in the example on the right, we are tracking to an interface. So we're moving we're moving higher order mesh elements to track the unstable interface. And as of MFEM version 4.3, this runs on the GPU. All right, well, can you go back to my other slide then? I guess we can show the movies. The other presentation, thank you.
Oh, sorry, we'll have to.
That's all right, no problem.
We had difficulties to get these slides to work.
It looks like it's starting to animate. Okay, yeah, and I just wanted to conclude with some acknowledgments. So there are many people that have contributed to this work, and I just wanted to take a moment to put their names up on the screen. So with that, I will conclude, and if there's time for any questions, I'd be happy to answer them.